So this is, we actually have donors who occasionally provide money for students in the form of scholarships, you know, a couple $100, $1,000 or whatever. But often they designate, you know, they'd like it to go to a particular student who was heavily involved in Boy Scouts, or does a lot of work in the community, or for a particular religious organization or something like that. So if you could fill this out, I can't guarantee that you'll get any money, but if we get gifts like that, I'll make sure that they're directed appropriately. So try to embellish as much as possible without lying. Okay, without flat out lying. How's that? So. Actually, most of our scholarships are typically to juniors, so that's why I'm doing that in this class. So, it's too late for you, Rodney. So. Fill this out if you want. It's primarily for juniors, but yeah, I'll collect them if you're done. If you're not interested, you got enough money then, huh? For sure. I did see that the university is going to be testing, or you can optionally get tested before leaving for Thanksgiving. I would encourage you to do that in an effort to help protect your families. So, I guess it's supposed to be rapid test, right? So you can find out the result, but not highly accurate, but you can find out the result quickly, and then if you do get a positive, then you can go for a more accurate test. So I want to finish up. The last topic that we'll cover is on sampling. And this is actually the first topic in EE310 next semester. For those of you who are electrical engineers, should be taking that class. It bridges the gap between continuous time signals and discrete time signals and discrete time signal processing. So if we have a continuous time signal, we can generate a discrete time signal, and it's sometimes just called a sequence. And we typically use bracket notation to differentiate between discrete time signals and continuous time signals. The bracket notation may actually remind you of array notation in a programming language, and that's intentional. It's typically these, when you sample, you get a sequence of numbers that can be stored in an array. The relationship, the way between the two is one way to generate a discrete time sequence is to actually sample a continuous time signal related where TS is the sampling interval or time. The sampling frequency is 1 over the sample interval. And so this would be if you're sampling at 1 millisecond per sample, the sampling rate or sampling frequency would be 1,000 hertz or 1,000 samples per second. Some common sampling rates and corresponding sampling times is in the telephone system. The original telephone system used to be analog from endpoint to endpoint, even across the country. But these days, it's primarily, if you still have a landline, it's primarily just digital from your home to the nearest exchange, and then it's actually, that analog signal is converted to a digital signal at that point, and then maybe sent around the country. Actually, even the cellular telephone system still uses the traditional landline infrastructure. I mean, when you communicate via cell phone, it's just from your cell phone to the nearest tower. And then the towers are actually connected using the traditional telephone network. So, but in that telephone system, they use a sampling rate of 8 kilohertz or corresponding sample time of 125 microseconds. They also use what's known as a 8-bit samples, or an 8-bit byte per sample. CD quality uses a much higher sampling rate, well, over 5 times higher sampling rate, 44.1 kilohertz, or 44,100 samples per second. So it's 22.67 microseconds. So here's a simple example. Where we have a cosine sinusoid, and I write it like this so that you can see that it's 1,000 hertz sinusoid, or 2,000 pi radians per second, is sampled at a frequency of 8 kilohertz, or 8,000 samples per second. What is corresponding sequence. We can find the sequence for different values of n by just replacing t here with nts or n over fs. So in this particular case, it's cosine pi for n. And you could, so at n equals 0, the first sample would be cosine of 0, okay, which is 1. When n is 1, cosine of pi over 4 would be 1 over square root of 2. When n is 2, it would be cosine of pi over 2, or 0. So what that would look like, so the red here is showing this 1000 hertz sine wave, cosine wave, and you can tell it's 1000 hertz because it has a period of 1 millisecond, right? So that's the continuous time waveform in red. Okay. If we're sampling at 8,000 samples per second, then we would get 8 samples over a period, and they're equally spaced here. So here's the period at 1, right? N equal to 0, and we get a 1. At n equal to 1, that would be 1 over the square root of 2, or 0.707. Here's n equal to 2, so cosine of pi over 2, so that's 0, and so on and so forth. And then this would be x of 3, x of 4, 5, 6, 7, 8, and then the cycle just starts over again. But this would be the sequence of numbers here on the green lines, and typically discrete time signals are displayed showing that green line, those green lines like that. In MATLAB and Octave, you can create a plot using what's known as the stem function instead of the plot function. It'll create a stem plot, which just shows those lines, allows you to graphically see the sequence. Okay, I guess the question is, when we sample signals like this, sample an audio signal, eventually we have to convert it back to an analog signal. That's what we hear, that's what we see. So the question is, when we sample signals like this, do we lose information? Or how fast should I sample to ensure that I don't lose information? So that when I convert back to this analog signal, I get a true representation of the original signal. So there's a sampling theorem, and we'll actually see where this comes from today. It's another application of the Fourier Transform. But it says if x of t is a low pass signal with maximum frequency of b hertz, we can recover x of t, the continuous time signal, from x of n, from the sequence, if fs is greater than 2 times that highest frequency. Okay, or 2 times b. This minimum sampling rate, this 2b rate, is called the Nyquist rate, N-Y-Q-U-I-S-T. So I've mentioned in the past that for voice, the highest frequency in a voice signal, speech, is about usually around 3.5 kilohertz. Okay. So according to the sampling theorem, we should sample at least 7 kilohertz to reconstruct the voice from the samples. telephone company actually uses 8 kilohertz. There is a reason, and we'll see that again a little later today, why you would want to sample at a rate that's higher than the Nyquist rate, the minimum rate. So the phone company does that a little bit. Similarly for audio quality, we talk about music. The highest frequency that you can hear in music, and it depends a little bit on your age. When you're younger, you can hear higher frequencies. Women can typically hear higher frequencies than men. So men typically have an upper frequency of about 15 kilohertz. As you age and your eardrum stiffens, you lose the ability to hear high frequencies. Women can typically hear highest frequencies up around 18 kilohertz. But if we just round up to 20 kilohertz, according to the sampling theorem, to recreate these music signals, we need to sample at least 40 kilohertz, right? CD quality is 44.1 kilohertz. So again, they exceed the Nyquist rate a little bit. To get an idea of where the sampling theorem comes from, we're going to look at what's called ideal sampling. Although it's ideal, which means you can't really do it in practice, it's mathematically simple, and it gives us a lot of insight into practical sampling. And actually, talk about practical sampling. It's a modification of this ideal sampling method. So I'm going to define a new signal, delta subscript t of s of t, which is an infinite train of impulses. So we've talked about delta not being a practical signal or a real world signal. Certainly an infinite number of them wouldn't be real world signal, but this is just representing a sum of impulses, all ts apart, right? So with n equal to 0, we get delta t, which is this one, all with a weight of 1. With n equal to 1, it would be an impulse just shifted to the right by ts. So that summation notation is just a convenient way to represent a periodic waveform as a sum, as an infinite sum of shifted signals. We form a sampled signal xs of t by multiplying x of t and this impulse train. And this is the definition of ideal sampling. Or going back into my summation notation, moving x of t inside the sum, and then using the multiplicative property of the impulse, we would get x of nts delta t minus nts. But this is just our sequence values times our impulse train. So I've got a better picture of that. So this is, ignore the right-hand side for just a minute. We'll get to that. But here's our continuous time signal. Here's this infinite train of impulses. And when we multiply the two together, in the green here, would be the infinite train of impulses. Again, but instead of having a weight or amplitude of 1, they would actually be weighted by our sample values at that instant. And so the original continuous time signal is now shown as a dashed line. So in between the samples, we have 0. This is still a continuous time signal, right? We've treated this impulse, even though it's not a realistic signal, it is a continuous time signal. So to proceed or figure out where the sampling theorem comes from, we actually want to look at what's going on in the frequency domain. Fourier transform of xs of t can be found using, so it's the Fourier transform of the product of our original continuous time signal and this impulse train. So in the frequency domain, that product becomes the convolution of the Fourier transform of our continuous time signal and the Fourier transform of this impulse train. So I'm going to call that delta TS of F. And that's what we've got to figure out now. What does the Fourier transform of this? Okay, what's that look like? That may, I don't know if that's on your Fourier transform sheet. I think it may be. It's actually just a couple of steps to get there to compute the Fourier transform of this. The sequence of steps is, this is periodic, so first express it as a Fourier series, an exponential Fourier series, and then find the Fourier transform of that. Going through that process has the steps in the book again, but I'm not going to take the time to do that. Delta TS of F can be shown to be TS of F is F of S, sum n equal minus infinity to infinity, delta F minus NFS. Kind of a surprising result, because this is an infinite train of impulses in the frequency domain that are all spaced Fs apart. And it's one of the few, I guess, signals that kind of has the same functional form in both the time domain and the frequency domain. So here at the top, this is supposed to be the Fourier transform of x of t, x of f. Okay, so Fourier transform of our low pass signal. When we take the Fourier transform of our impulse train in time, we get an impulse train in frequency. The impulses are separated by Fs, and they actually now have a weight of Fs. They're all multiplied by the sampling frequency. Okay. So xf of f, this is kind of nice because we have to do this convolution, and we typically avoid convolution except when we're convolving with an impulse, right? Then the convolution is trivial, because when you convolve with an impulse, it just shifts the function to the location of the impulse. So xs of f would be fs, the sum n equal minus infinity to infinity of x of f convolved with each of these impulses, or f of s minus infinity to infinity, x of f minus nfs. Okay. So this is the Fourier transform of the ideally sampled signal of this guy here on the bottom. But what it says, again, that's the summation of shifted versions of x of f, the low pass or baseband spectra. You know, with n equal to 0, I could expand the sum. At n equal to 0, I have fs times x of f. With n equal to 1, I have plus fs times x of f minus fs, which would just be the spectrum shifted to the right. So these are all called replicas of the original spectrum or Fourier transform. So this is the Fourier transform of this ideally sampled signal. It consists of copies or replicas of the baseband spectra shifted by fs, 2fs, 3fs, 4fs, on out to infinity. And then with n equal to -1, it'd be minus fs, minus 2fs, so on and so forth. And then there's actually this multiplication by fs, which is just a scale factor. So it says this ideally sampled signal actually has an infinite bandwidth. But it provides a clue as to how we can recover this signal, the original signal, from the ideally sampled signal. And we can do that just by low pass filtering. Removing the replicas would take us back from this theoretical ideally sampled signal and get us back this original analog signal, at least in theory. So I think that's the next figure here. So we can go from x of t to our sample version by just multiplication. If we low pass filter, then looking at the frequency domain, we'll recover our original x of t now. And you wouldn't build a system that does this, that goes from x of t to x of t. The idea is you would sample, store the sequence in a computer or on a CD, or transmit it over the internet. And then at the destination is where you would do this operation, low pass filter, and then recover the original signal or a duplicate of the original signal. Now there is back up. Not that far. I made an assumption here. Notice that the bandwidth of our low pass signal is B. B is the highest frequency in the signal. Now, I haven't talked about any sort of relationship between FS and B or TS and B, other than to say we're sampling at a TS rate or 1 over FS rate, right? Now that whatever rate we sample at determines, the spacing in time and then correspondingly the spacing and frequency. Notice the smaller TS would get here, the farther apart my replicas would be, okay? Because FS is proportional to 1 over TS. So the smaller my sampling interval, the more samples per second, the farther apart my replicas are in the frequency domain. But there is this condition here that in order to recover this guy, I need to make sure that they're not overlapped, right? It's really the sum of all these guys together. So the condition to prevent overlap is that this frequency would be Fs minus B. I have to have Fs minus B has to be greater than B, right? If that's not true, then this replica would overlap the previous. So that I require fs minus b has to be greater than b, or equivalently, fs has to be greater than 2b, which is the sampling theorem. Okay. And that's necessary to recover our original spectrum and recover our original signal. If we don't meet that condition, I actually get a distorted version of the original signal, or what's called an aliased version of the original signal. Okay, so and that's what I think. So although this is true for ideal sampling, it's true for practical sampling as well. Okay. So this is showing my original spectrum. This would be showing the spectrum when I'm undersampling. And then these things overlap. Now, really, what's shown here are the individual replicas, but really what I have is the sum of these. Okay, so where they're overlapping, what should really be drawn is actually the sum of these. Here, there's no overlap in this section, but here they're overlapping. Okay, similarly back here. Okay. I get this overlap. Now, if I low pass filter, what I'll recover is, this. If I low pass filter right at that frequency, I'll recover this, which is not my original spectrum. Right? It's a distorted version of my original spectrum. So I'll recover a distorted version of the original signal. Now, the distortion gets worse as fs gets smaller. There's more overlap in the replicas. So as fs gets smaller, again, that means my sampling interval is longer. Okay, so, well, intuitively, you might expect I'll do better recovering the original signal by sampling more frequently, right? With a higher sampling rate, a higher f of s, or a shorter sampling interval. And that turns out to be true, and you can see that in these figures, what's going on with regard to the spectra. Okay. Here's where fs is just equal to 2b, and the replicas are just touching. And so if I had an ideal low pass filter, I could run this through that low pass filter and recover that replica and filter out everything else. But that's the same spectra as my original. The advantage of oversampling is that my replicas are farther apart. So I can use instead of an ideal brick wall filter, something like a Butterworth filter that we've talked about, a practical filter. And because there's greater separation here, I can still do a good job of recovering my baseband replica. Okay, I want to talk a little bit about this phenomenon where we undersample, and it's called aliasing. It's pretty easy to explore the effects of aliasing if we think about sampling of sinusoids. So let's look at that case. Let x1 of t equal cosine of 2 pi 400p, and f of s is 1,000 hertz. Now x1 of t consists of a single frequency at 400 hertz. So from the sampling theorem, I would need to sample that at least 800 hertz. Well, we're sampling at 1,000, so I'm good here. I'm oversampling. Okay, that's okay. So if I look at my x1 sequence, it would be cosine of 2 pi 400 over 1,000 n, or the sequence that I would get is 0.8 pi n by sampling this 400 hertz sinusoid at a rate of 1,000 samples per second. Now let's think about a different sinusoid at a higher frequency, 1400 hertz, sampled at 1,000 hertz. Okay. So this is undersampled. Okay. So I shouldn't do this. I'm going to see why I shouldn't do this. But now if I plug in and find out my x2 of n sequence, cosine of 2 pi 1400 over 1,000. Maybe I should have you actually do these numbers on your calculator, but I'm going to do a little bit more math. This would be 1.4 n, or cosine of 2.8 pi n. But I can write that as cosine of 0.8 pi n plus 2 pi n. And cosine is periodic, right? So a shift of 2 pi or a multiple of 2 pi gives me the same value. So cosine of 0.8 pi n plus 2 pi n is the same as cosine of 0.8 pi n. Which is exactly the same sequence I have for x1 of n. Now this isn't some sort of mathematical, trickery. Again, if you plug this value, if you evaluate this at n equal to 100, 2 pi, someone have your calculator, put it in radian mode. No one have a calculator. Put your calculator in radian mode. We'll verify that these are exactly the same, that this expression and this expression are exactly the same for two arbitrary values of n. Okay, so let's say n is equal to 13. Okay, just make sure your calculator is in radian mode. But calculate cosine 2 pi 400 times 13 divided by 1,000. And tell me what you get.
Like
0.309. And then now do the 13th sample of x2. So just recall and change the 400 to 1400 and 0.309, right? Now, there was nothing special about 13. You could pick any number. What's really going on here with this undersampling case is here, and this is a figure from the textbook, and he actually used two different frequencies than I did in my example. But you could have done the same thing. Here in the blue, we've got 100 hertz sinusoid, and we're sampling at 1 millisecond, kilohertz rate. So that's fine. The blue curve is 100 hertz. We're sampling at a kilohertz. the Nyquist rate is 200 hertz. So we're oversampling. We're actually getting 10 samples over a period of the blue waveform. The red waveform is a 900 hertz sine wave. We're sampling at 1,000. For 900 hertz, we need to be sampling at 1,800 hertz or more, okay, but we're undersampling. But notice what happens when I sample both these at a 1 millisecond rate. At those instances in time, the 900 hertz and the 100 hertz sinusoid are at exactly the same point. Okay. Now there's lots of other stuff going on with the 900 hertz sinusoid in between, but I'm not sampling in between. I'm only sampling at every 1 millisecond. So it wouldn't matter whether I sample this 900 hertz signal or the 100 hertz signal. If I sample at this 1 kilohertz rate, I'm going to get exactly the same sequence. So what the sampling theorem tells us is what do we need to do to recover from my sequence the original continuous time sine wave? Now with this particular sequence, there's no way to know whether it was actually from sampling a 100 hertz signal or sampling a 900 hertz signal. There's actually an infinite number of different frequencies that would give me the same sequence. There are no frequencies that satisfy the sampling theorem other than the 100 though. Okay. So if I sample 100 at a kilohertz, I'm okay, but 900, I'm not. I'm undersampling, and I get the same sequence. There are other higher frequencies above 900 hertz, which I would sample and still get the same sequence. So I have to rule those out. That's why we have the sampling theorem. It says as long as I sample, so what if I had a signal that was the sum of these two, the 100 and the 1900? Then I would need to sample at least 1,800 hertz, right? 1.8 kilohertz. So I would get at least 2 samples per period of my 900 hertz. Okay. That's going to give me multiple samples of my 100 hertz, okay, but the sequences would be different in that case. It's only when I sample at this particular case at this 1 kilohertz rate where I generate exactly the same sequence. So if we follow the Nyquist criteria, we'll ensure that that doesn't happen. And actually, so what would happen if you undersampled? We generated this sequence back at by sampling a 900 hertz signal. Then we converted that back to a continuous time, assuming that we satisfied the sampling rate. This 900 hertz signal would appear as a 100 hertz tone. It's said to be an alias of the 100 hertz tone. And you've probably seen visual evidence of undersampling in movies or commercials where there's either an old westerns, it was common, with a wagon wheel and the spokes were spinning. You'll see it on some car commercials when you look at the wheel, and the rims have spokes, or maybe 8 spokes coming out or something, and the wheel appears to be turning backwards, right? Or at a different rate, it just looks odd. That's because the frame rate at which they're sampling is much lower than the rate at which the tire is turning. Okay? I think In movies, high def, I think they sample at 60 times per second or something like that. It may be 120 times per second. But it doesn't satisfy the sampling rate for the, according to the frequency at which those wheels are turning. So they actually appear as a different frequency, appear to be turning at a slower rate, or even a negative frequency, appear to be turning backwards. What's going on there? So that's a visual verification of undersampling that occurs in movies. This is where we'll end. Okay, so this is the end of chapter 6. So we'll review on Monday for our exam on Wednesday. I'll post a practice exam for you to work on over the weekend. We can review that on Monday. Okay, so look on the website for that practice. And turn in these sheets if you haven't already.
Can I put stuff that I didn't?
Huh?
Can I put stuff that I did in the past?
I think it's probably better stuff that's current now, but I mean, certainly I'd put down if you're involved in Boy Scouts or something like that, that's fine. Sometimes you'll get awards for like specifically for Eagle Scouts. If I get everyone's,
Yeah, I'll put it.
did I get them all?
Maybe put an Eagle Scout on there too.
Oh yeah, that's important. What was your project?
Well, kind of had to be two. First one didn't really work out. So the first one, I was going to go to Henderson and build a enclosure for skunks for the animal rehabilitator. And then it didn't work out. So I just had that and switched it and relocated my house.
Did what?
I redid a playground.
Okay.
So I took a weed gravel out and I put down a weed barrier and then I brought in. Actually, I took a mulch out and then I brought a weed gravel to check it all out.
Where was that at? In Henderson?
No, it's at from the west side by Franklin, the Sacred Heart Church.
Okay.
That's where I went to preschool at.
You had that lousy playground too.
I know.
Good now that open.
Mulch on there, get all the splinters.
Yeah.
It was preschool, so
I think I forget Eagle Scout related that. I don't know what to put it with, because I'm not active anymore, but I put it in leadership slash.
Doctor ended up calling at the end of class. I might be going back on the steroid.
Oh. I don't know. Maybe
The-
feel better.
So, well, they put me on 3 different types of medications. And one of them was a steroid, one of them was like just a straight up anti-itch, which makes you extra drowsy.
Yeah.
Well,